In this video, we're going to talk about counting, and this is in preparation for our discussion of probability. So in many real-world situations, we need to determine the probability of an event's occurrence. In other words, how likely that event is to occur versus another event. So knowing likelihood requires counting possibilities for that desired event and other related events. In other words, we want to think of each event as being a possible outcome from taking a certain action. So if we take a certain action, we perform a certain operation or a sequence of operations, there's a specific number of possible outcomes. Each of those outcomes is called an event. When we talk about probability, what we want to know is how likely is any one possible outcome or any combination of outcomes versus the other outcomes based on the action we're taking. Well, first thing we have to know in any situation like this is how many different ways could our particular operation go? How many different ways can we get an outcome? How many different outcomes are there in total? And then we can relate specific outcomes to the total number of outcomes, and we're going to define that as the probability of any particular event happening. So what we're going to talk about here is the fundamental counting principle, which is going to allow us to deal with a lot of situations where we're performing a sequence of actions or a sequence of operations. So the number of ways in which a series of successive things or operations can occur is found by multiplying the number of ways in which each individual thing or operation can occur. In other words, if you have n groups of items, think of those as the individual outcomes for each individual operation you're performing. We're going to call those m sub 1, m sub 2, all the way to m sub n. So those are the number of different ways we can accomplish each individual operation. So each of these items are in each group. So the number of ways you can choose a single item from each group is going to be the product of each of those individual numbers. So m sub 1 times m sub 2 times all of those numbers all the way up to m sub n. So we can think of this as different outcomes for taking an action or different choices. Suppose we have 10 choices for a certain thing. If we want to choose one thing and then choose from another group, we multiply the number of ways we can make each individual choice, and that represents the total number of possibilities for how we could make a bunch of different choices. So, for example, a restaurant offers 6 appetizers and 14 main courses. In how many ways can a person order a 2-course meal? Okay, so what we need to do first is we need to think of this as a sequence of operations. We have to think about the physical actions that are being taken in any situation like this. So what are the actions being taken here? Well, we actually have 2 of them. Action or operation number 1 is choosing an appetizer, and action or operation number 2 is choosing a main course. Well, there's 6 ways to perform action 1, 6 possible outcomes for making a choice of an appetizer, and then there's 14 possible outcomes for making a choice of a main course. So the fundamental counting principle tells us if we want to make both of these choices at the same time, if we want to choose an appetizer and we want to choose a main course, we just multiply together the number of ways that we can accomplish each of those individual actions. So 6 possibilities for choosing an appetizer times 14 possibilities for choosing a main course, which results in 84 meals in total. Think of it this way. Think of it as for each individual appetizer, you could choose from the 14 options. So for appetizer number 1, you could choose one of the 14 main courses. For appetizer number 2, you could choose one of the 14 main courses, so on and so forth for all 6 appetizers. That's just a way of modeling multiplication. So what we're illustrating by thinking of it that way is multiplication. We take 6 of the appetizers, each 6 of those, and we can match up each of those 6 to the 14 different main courses. So if we multiply 6, the number of ways we can do operation 1, times 14, the number of ways we can do operation 2, then that gives us the total number of combinations we can get for this 2-course meal, which in this case is 84. Okay, let's look at another example. Next semester, you are planning to take 3 courses, math, English, and history. Based on time blocks and highly recommended professors, there are 8 sections of math, 5 sections of English, and 4 sections of history that you would be willing to take. Assuming there are no scheduling conflicts, how many different 3-course schedules are possible? Okay, so again, we want to go back to operations, actions being taken. What are the actions we're taking here? We're taking 3 actions. Number 1 is choosing a math course. Number 2 is choosing an English course. And number 3 is choosing a history course. The number of ways we can choose a math course is 8 because we have 8 different choices that we can choose from. We have 8 different sections of math that we can potentially choose from. The number of ways to choose an English course is 5 because there are 5 different English courses to choose from. And the number of ways to choose a history course is 4 because there are 4 different history courses to choose from. If we multiply 8 times 5 times 4, the number of ways to accomplish each of those individual steps, then that gives us a total of 160. So there are 160 ways to choose one of those 3 courses and to create a schedule. What we're going to notice is that the numbers get really, really big, really, really fast. That might seem surprising to you, the fact that you're only choosing 3 courses, but there's 160 different possibilities. That's 160 different unique schedules that you could choose if you're going to take those 3 classes. Well, imagine you're taking 5 different classes, and imagine there's a lot more than 8 sections, 5 sections, 4 sections. The numbers get really, really big, really, really fast. That's going to be very much evident in the next example we look at. Also, I can't emphasize enough, you have to think about the actual physical action being discussed in the situation. What are you actually doing? Think about it as a step-by-step process. You have to think about what each step in the process is and think about how many ways you can accomplish each step. You're going to take the product of how many ways you can accomplish each of those individual steps. Okay. So the next example, you are taking a multiple choice test that has 10 questions. Each of the question has 4 answer choices with 1 correct answer per question. If you select one of these 4 choices for each question and leave nothing blank, in how many ways can you fill out a test? In other words, another way to think of this is if you were just going to randomly choose answers, how many different ways could you select answers for this 10-question test? Okay, now here's where it would be very easy to make a mistake. There are 2 obvious numbers in this problem. The 2 obvious numbers are 10 and 4. It's very tempting to say that you would take 10 and multiply it by 4, but that's not actually representative of the situation being described. That would be like saying you're choosing one of 10 questions. In other words, you have 10 to choose from, you're choosing one of 10, and then you have 4 answers to choose from, you're choosing one of 4. That's actually only a sequence of 2 steps. That's making 2 choices. That's not really what's going on here. What's going on here is you have a test with 10 questions. So this is actually a 10-step process. For each of those individual 10 questions, you have to choose an answer choice. Well, each question has 4 choices. So in other words, you have a 10-step process, and each step in the process can be accomplished 4 different ways. So in other words, you're multiplying 4 by 4 by 4 10 times. Each of those 4s is represented by, or is representative of the number of ways you can answer each of those questions. So if you multiply 4 by 4 10 times, that represents the number of ways you can fill out that test. Now, another way of saying 4 times 4 times 4, so on and so forth, 10 times, is actually with an exponent. Why is that helpful? Well, rather than having to type 10 4s into your calculator, you can type 4 to the 10th power, and it's going to accomplish the same thing in a lot less time. So how would you type 4 to the 10th power into your calculator? Well, remember the up arrow. It may be on this location if you have this calculator. If you have a different calculator, it may be somewhere else, but you're looking for something that looks like an up arrow, or it may say something like x to the y power. It may have an exponent as a symbol, something like that. That's the kind of thing you're looking for. So we're going to type the base first, which is 4, and then it is raised to the 10th power. And then I'm going to hit enter, and that gives me the answer. This is a surprisingly big number. Think about what this is. So if you start on the right and count by 3s, that'll tell you what place we're in. So there's 3. takes us to 576. There's 3, takes us to 048. So what that tells us is this is in the millions place. So 1,048,576. That is the number of ways you can actually fill out this multiple choice test. So with only 10 questions on your test and 4 choices per question, there are over 1 million ways to fill out a test. That's kind of surprising, right? It doesn't seem like it would be that high, but it is. Again, if you think about it the way we think about the appetizers and the main courses, you have 4 choices for question 1. Well, each of those 4 choices could then be matched up to 4 choices for question 2, 4 choices for question 2, 4 choices for question 2, and so on and so forth, 10 times. So by the time you match up all the different possible combinations, you have over 1 million different ways to choose a unique set of answers. So one possibility is that you choose A for every question. You could choose B for every question, or C or D. Those are 4 possibilities out of the total. Maybe you choose A for the first 9 and then B for the second, or C for the second, or D for the second. Each of those different combinations is considered when we talk about the number of ways we could fill out that test. And when we look at the total number of ways, it's going to be 1,048,576 ways. Okay, let's look at a couple more. Now again, you have to go back to what are the actual operations, what are the actions, what are the steps in the process, and how many different ways are there to accomplish each step. So for a temporary job between semesters, you are painting the parking spaces for a new shopping mall with a letter of the alphabet and a single digit from 1 to 9. The first parking space is A1 and the last parking space is Z9. What we want to know is how many parking spaces can you paint with distinct labels. Another way of saying this is how many different combinations are there if you're going to choose a letter and if you're going to choose a digit from 1 to 9. So this is a 2-step process. Think about each space you paint. You paint a letter, you paint a number. So in terms of painting a letter, you have 26 letters to choose from. So there are 26 ways to do step 1. And then in terms of the number, there are 9 digits to choose from. So you have 9 ways to accomplish step 2, which is painting the number. So 26 ways to do step 1 times 9 ways to do step 2 is going to be 234 distinct combinations. So that means you could paint 234 parking spots using just a letter and then using a digit from 1 to 9. Okay, let's look at another one. Telephone numbers. Telephone numbers are where numbers get really, really big. How do we have enough telephone numbers to cover everyone in the United States and everyone in the world? Well, it's because we have so many digits. International numbers have even more digits than we do. So the more digits you have, the more possible phone numbers you have. So let's see if we can determine how many different phone numbers we can come up with. Okay. So telephone numbers in the United States begin with a 3-digit area code, followed by 7-digit local telephone numbers. So area codes and local telephone numbers cannot begin with a 0 or a 1. So under these conditions, we want to know how many different telephone numbers are possible. So we can break this down into 2 steps, or we can even break it down further. If we're going to think about it as 2 steps, think about the area code as being 1 step, so choosing an area code, and then choosing a local number is another step. And then from there, we'll break it down a little further. So step 1, choose your area code. Step 2, choose the local number, which is 7 digits. So the area code is 3 digits, the local number is going to be 7 digits. What we want to know is within each of those choices, how do we choose all the different digits? So in total, we're talking about 10 digits. Now we have some limitations. So notice it says that area codes and the local numbers cannot begin with a 0 or 1. So the rest of the digits we don't have any limitations on, but we can't start an area code with a 0 or 1, and we can't start a local number with a 0 or 1. So for our area codes, for the first digit, think of it as a 3-step process for the area code. We're choosing 3 numbers. For the first number we choose, we can't choose a 0 or 1. So we can choose 2, 3, 4, 5, 6, 7, 8, 9 for a total of 8 possible choices. Now, once we go to the second and the third digits, there aren't any limitations. So those we can include 0 and 1 as possible choices. So for the second digit, we have 10 numbers to choose from. And then for the third digit, we also have 10 numbers to choose from. So 8 choices for the first digit, 10 for the second, and 10 for the third. Multiply those together, and we have 800 different possible area codes. Now, for the local number, we're choosing 7 digits. Now, we have the same limitation on the first digit. So the first digit cannot be a 0 or a 1. So again, we have those 8 choices for that first digit. So 8 choices for the first, and then we're choosing 6 more digits. There are no limitations on the others. So for the additional 6 digits, 10 choices, 10 choices, 10 choices, 10 choices, 10 choices, 10 choices. Now, just like with the multiple choice test, if we're multiplying a sequence of the same number over and over and over again, an easier way to represent that might be with an exponent. So in this case, we have 6 tens because we're choosing 6 digits, and we have 10 options for each digit. So another way to represent that is going to be 10 to the 6th power. So in terms of just the actual telephone number, not with the area code, but just the actual telephone number, it's 8 times 10 6 times. Another way of saying that is 8 times 10 to the 6th power. So let's put that into the calculator. So 8 times 10 to the 6th power. So when your calculator evaluates this, it's going to do the exponent first, and then it's going to do the multiplication. So when we press enter, again, you may have to count your digits. It's helpful to do that to see how big this number really is. So 3 zeros, and then 3 more zeros, and then the 8. So that is going to be 8 million. So there are 8 million different local telephone numbers. Now, there are more than 8 million people in the United States. So how are there enough telephone numbers to go around? Well, that's where the area code comes into play. So for each local area, we have 8 million options. So think about just Houston. We have area codes in Houston. And then within each of those area codes, we can assign 8 million different local numbers. We're actually going to talk about that in the next example. Each of those 8 million local numbers can correspond to each of those 800 area codes. So say we have an area code of, 200, 200. Well, 200 can match up with any of those 8 million numbers. 201 can match up with any of those 8 million numbers. 202 can match up with any of those 8 million numbers. So we can recycle the local numbers as long as we assign them to a new area code. As long as the area code is different, then we have a new telephone number overall. So we've chosen area codes. There's 800 ways to do that. And then we've chosen local numbers. There's 8 million ways to do that. So in terms of choosing a whole telephone number, which has to have both of those, step 1 is choosing your area code, and step 2 is choosing your local number. So if we multiply the number of ways we can do that together, then we get the total number of telephone numbers. So 800 area codes times 8 million local numbers. Now double check, particularly with these numbers where you're typing a lot of zeros, make sure you typed the actual number of zeros you intended. So count your zeros. So from the right we have 3, and then 3 more, and then the 8. So that is an 8 million, and then we're multiplying by 800. So I press enter, and it's going to be a ridiculously large number. Now what is this? Again, count your zeros. So 3 zeros, that takes us to thousands. 3 zeros, that takes us to millions. 2 zeros and a 4, which then takes us to billions. So that is 6,400,000,000. numbers. That's actually the number of phone numbers we could come up with here in the United States just using our area codes and using our local numbers. Now, there's nowhere near that many people in the United States. So what that means is that we're not going to run out. Now, also, as people pass away, eventually their numbers go back into circulation. I want to say it usually takes a couple of years, but eventually numbers are recycled as well. So telephone numbers that have been already used are then recycled to a new telephone user. But because we have so many options and because we recycle, there's no way we're going to ever run out of telephone numbers. Now, what if we did? What if we did run out of telephone numbers? The easiest way to overcome that would be to add on an additional digit. So if we were to make local numbers a little bit longer, or if we were to make the area code a little bit longer, we then can take this number and multiply it by 10. The additional digit we choose has 10 possibilities. So if we wanted to choose additional digits, each additional digit would allow us to take the total and multiply it by 10. Say we were to do that. If we were to take this number and multiply it by 10, it would go from 6.4 billion to 64 billion. So in other words, as long as we don't have to meet 64 billion requirements for telephone numbers, then we'd be good to go. So odds are we'll never have to do that, but if we did, that would be a way to come up with more numbers. Okay, let's look at the same example with a slightly different context. What about Houston? So all phone numbers assigned to the Houston metro area have an area code of 281, 346, 713, or 832. How many phone numbers are possible for Houston, assuming that the first digit of the 7-digit local number cannot begin with 0 or 1? Okay, so what's the same, what's different? The way we choose a local number is going to be the same. So we still choose from 8 digits for the first number, and then we can choose from all different 10 digits for the last 6 numbers. So then the way we can choose local numbers, there's still going to be 8 million ways to choose a local number. Now what changes here is how we're choosing an area code. We want to specifically create a number that's going to go to Houston. There are 800 total area codes, but in the Houston area, how many do we have? Well, we only have 1, 2, 3, 4. So again, if we're going to think of this as a 2-step process, number 1, step 1, choose your area code. There are only 4 ways to accomplish step 1 because there's only 4 area codes to choose from. Now there's still 8 million ways to do step 2 because there's still 8 million ways to create a local number based on the requirements that we not start with a 0 or 1. So in the Houston area, we choose the area code, 4 choices for that. We choose a local number, 8 million choices for that. If we multiply them together, then we have 32 million numbers. So again, more than likely that's enough phone numbers to cover us for a long time. I want to say the Houston area is still under 6 million. And again, we recycle numbers as people pass away. So we continue to recycle numbers, but assuming we didn't, we still have 32 million unique numbers that we have to use up before we'll actually run out. So more than likely, we're not going to run out of telephone numbers anytime soon. So this is the fundamental counting principle. We take a sequence of operations, identify how many different ways there are to do each step in the sequence, multiply how many ways there are to do that by how many ways there are to do step 2, how many ways to do step 3, so on and so forth. That total is going to give us the total number of possibilities.